For quite a while, people have envisioned what life might resemble in different universes. Thanks to the James Webb Space Telescope, the most remarkable telescope in existence, that question can finally be investigated. While observing the nearest star system to us, Proxima Centauri, which is only 4 light-years away, researchers have noticed some unconventional anomalies from one of the planets in the system, Proxima b. These oddities, called artificial lights, have puzzled some of the best minds in the scientific community. But what are they? Do these lights suggest the presence of intelligent life on the planet? Join us as we explore the James Webb Telescope's unnerving discovery of city lights that could change everything. The only life that we are currently aware of exists on Earth. Since the beginning of civilization, humans have wondered whether there is life elsewhere in the universe. To address this, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence SETI project in 1984. The non-profit's goal is to gather spaceborne radio transmissions. Radio waves can travel farther, and are thus more likely to be detected by the 42 radio telescopes that make up the Allen Telescope Array in the Californian Outpouring Mountains. However, in the past 30 years, no definite alien transmissions have been found. Following that, the James Webb Space Telescope's successful launch has advanced the search for life by enabling the study of unseen planets orbiting distant stars. As the largest telescope in existence, floating approximately 1 million miles from Earth and equipped with extraordinarily sensitive detectors, it has the potential to uncover significant discoveries. Decades ago, there were no known planets outside our solar system. Since then, more than 4,000 exoplanets have been discovered orbiting various stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial vegetation. For example, the Galileo spacecraft on its journey to Jupiter turned its instruments back toward Earth and detected a definitive sign of plant life by identifying the vegetation red edge, VRE biosignature, a combination of red and infrared light reflected by plants. A planet like Earth, covered in dense jungles, would emit a strong and easily detectable VRE signal. The James Webb Space Telescope, JWST, will measure the VRE of distant Earth-like planets in the habitable zone around stars, potentially offering significant indications of life in their atmospheres. When starlight passes through a planet's atmosphere, the JWST may be able to detect missing wavelengths through spectroscopy, as atoms and molecules in the atmosphere absorb specific frequencies, creating a unique fingerprint that the JWST can recognize. This method can determine the composition of an atmosphere and assess whether it might support life. Life could exist on Earth-sized planets with atmospheres similar to our own, dominated by oxygen, nitrogen, and carbon dioxide. By searching for elements that aren't typically present, we may even identify signs of advanced civilizations. For instance, chlorofluorocarbons, CFCs, used in refrigeration and cleaning products, would likely be noticeable to alien observers studying Earth's atmosphere from afar. If the JWST detected CFCs in the atmosphere of another planet, it would strongly suggest the presence of a civilization. However, life on exoplanets might not resemble life on Earth at all. Even natural organisms, such as extremophiles, microorganisms capable of surviving in extreme conditions like boiling temperatures or highly acidic environments, can appear alien. Since planets like Earth are more likely to support life than those with extreme conditions, it makes sense to start with them. Prime candidates for life would have temperatures that allow liquid water to exist on their surfaces and orbit stable stars. Our Sun, a yellow G-type star, is relatively rare and has a shorter lifespan compared to red dwarf stars, which are more common and have lower luminosities and temperatures. One of the JWST's first missions is to study the TRAPPIST-1 planetary system, located about 40 light-years from Earth. This system orbits a quiet red dwarf star and consists of 7 Earth-sized rocky planets. 3 of these planets, located in the so-called habitable zone, might have liquid water on their surfaces. Closer to home, the best chance of observing city lights outside our solar system is Proxima Centauri. A red dwarf star located 4.25 light-years from the Sun. Proxima is much fainter than the Sun, so a planet would need to be much closer to it, about 5% of Earth's distance from the Sun, to support life. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable zone, known as the Goldilocks zone, where the light intensity is just right for liquid water. Proxima b, which orbits Proxima Centauri, might be an airless, dead planet because it orbits only 4.6 million miles from its star. This close orbit exposes it to strong solar winds that could destroy its atmosphere. However, Proxima b receives enough sunlight for temperatures and liquid water similar to those on Earth. Due to its proximity to its star, Proxima b is thought to be tidally locked, always showing the same side to the star, much like the Moon does with Earth. Proxima Centauri is only 18% the mass of the Sun and emits far less light. Despite its close orbit, Proxima b could sustain liquid water if it has an atmosphere to trap heat. Still, the planet isn't particularly hospitable to life. Its tidally locked nature causes one side to experience permanent daylight and the other perpetual darkness, leading to extreme temperature differences. Additionally, the planet receives 100 times more high-energy radiation than Earth does. The high-energy radiation from Proxima Centauri makes Proxima be a challenging candidate for hosting life as we know it. However, the potential for life on this planet cannot be entirely dismissed. If Proxima b has a strong magnetic field or a thick atmosphere, it could shield the surface from the star's radiation, creating pockets of habitability. The James Webb Space Telescope is capable of analyzing Proxima b's atmosphere for signs of such protection. By studying the starlight that passes through the planet's atmosphere, the JWST can detect chemical signatures that might indicate the presence of life-supporting conditions. For example, if the telescope identifies oxygen, water vapor, or methane, it would significantly strengthen the case for habitability. What has intrigued scientists the most about Proxima b are the mysterious artificial lights detected on its surface. These lights resemble the glow of city lights seen from space on Earth. While natural phenomena like volcanic activity or lightning could explain these lights, their regularity and intensity have led some researchers to speculate about advanced extraterrestrial civilizations. The search for artificial lights is not entirely new. Scientists have long considered the possibility that intelligent civilizations could leave detectable technological signatures. For example, the use of massive energy sources such as Dyson spheres or city lighting might be visible to telescopes like the JWST. Detecting these signatures would provide compelling evidence for intelligent life. However, the presence of artificial lights on Proxima b raises more questions than answers. Are they truly signs of an advanced civilization? Or could they have a natural origin? If they are artificial, how did this civilization develop under such extreme conditions? These questions fuel the excitement and curiosity of researchers, pushing the limits of what we know about life in the universe. Meanwhile, Proxima b is not the only target of interest. Other planets in the habitable zones of nearby stars, such as those in the TRAPPIST-1 system, offer exciting opportunities for exploration. The JWST will also focus on these planets, analyzing their atmospheres for biosignatures or technosignatures. As the JWST continues its mission, it is expected to transform our understanding of the universe and our place within it. Whether it finds definitive evidence of extraterrestrial life or not, the telescope's discoveries will undoubtedly reshape humanity's perspective on existence beyond Earth. For now, the lights of Proxima b remain a tantalizing mystery, symbolizing humanity's enduring quest to answer one of its oldest and most profound questions. Are we alone in the universe? Counting X-rays and ultraviolet light due to its proximity to Proxima Centauri, Proxima b is also bombarded with high-energy particles during stellar eruptions. Unless it has a protective magnetic field like Earth's, the conditions for life may not be favorable. However, reasonable circumstances could potentially make Proxima b a more habitable world. Unfortunately, models suggest that the atmosphere of tidally locked planets might be vulnerable to rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima b's volcanic activity or magnetic field strength, we cannot even speculate whether the planet has an atmosphere. However, since an atmosphere implies the presence of oceans, and the two together suggest the possibility of life, we are desperate to know if Proxima b has a complex environment. If it does, it could have solar panels covering the day side to generate power, lighting and warming the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima b has triggered a race to determine if it transits its star as seen from Earth. These transits would allow scientists to determine the planet's size and mass, enabling them to assess its density and confirm its rocky composition, thus providing information about the materials forming those rocks. During a transit, starlight passing through the planet's atmosphere could reveal its nature. However, the probability that the orbit aligns perfectly for scientists to observe a transit is just 1.5%. The star's tendency to erupt complicates matters. Astronomer David Kipping of Columbia University says the star is tricky, as stellar heat makes a rocky planet absorb sunlight and re-emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. Additionally, the James Webb Space Telescope, JWST, was specifically designed to study infrared light. Proxima b's infrared heat signature is key to detecting its atmosphere. Moreover, the infrared part of the spectrum holds great promise for Hubble's successor, which may allow the JWST to observe city lights on Proxima b's night side, even if they are as dim as those currently used on Earth. The JWST could detect artificial illumination as long as it is confined to a frequency band much narrower than the star's light. Proxima b's day side may be heavily covered with solar panels reflecting starlight. Since Proxima b orbits its star tidally locked, day and night are indistinguishable, with cool night lows following daytime highs. The temperature difference between day and night, however, depends on whether the planet consists entirely of bare rock. Both an atmosphere and ocean conduct heat. If there is no atmosphere, Proxima b's day and night temperatures will differ significantly. In fact, since the day side will emit all the energy it receives from Proxima Centauri as a blackbody, we can calculate the exact amount of blackbody radiation. The night side, on the other hand, would resemble a frozen wasteland. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, it will take the JWST only 11.2 Earth days to measure the infrared radiation from Proxima b's two hemispheres after completing its orbit around the star. If Proxima b has an atmosphere, the next step will be to analyze its composition. The presence of gases like oxygen, water vapor, and methane in particular could indicate habitable conditions, if not actual living organisms. However, to achieve this, we must successfully capture starlight as it reflects off or passes through the planet's atmosphere. An extremely challenging task. The JWST can closely examine only a few of the nearest potentially habitable worlds, as it was not built specifically to search for extraterrestrial life. It is limited to tracking changes in atmospheric concentrations of methane, carbon dioxide, and water vapor. The JWST cannot detect unbound oxygen, which is the strongest indicator of biological activity. Even if some combinations of these gases may suggest life, one of the planned ground-based observatories capable of conducting a thorough atmospheric analysis is the extremely large telescope, expected to begin operations in the 2020s. Ozone may be among the substances the JWST can detect. Until these telescopes are operational, the JWST may provide data to analyze for decades. More advanced space telescopes might use state-of-the-art techniques to block out the blinding brightness of a planet's host star, revealing starlight reflected from the planet. Similar to shielding a light source with your hand to see distant objects, future space telescopes could achieve this with small internal masks or large external umbrella-shaped satellites. After starlight is blocked, studying light reflected from a planet becomes much easier. Unfortunately, most gases released by terrestrial life can also be produced by non-biological factors. For instance, methane is emitted by both cows and volcanoes, and sunlight can convert water molecules into oxygen and hydrogen without photosynthesis. When searching for alien life, astronomers are certain to encounter false positives. Thus, Scientists must thoroughly understand a planet's geological and atmospheric processes to evaluate whether they resemble a biosignature and rule out false positives. The next wave of planetary exploration may yield undeniable evidence to establish the existence of life. The James Webb Space Telescope's foundational data gives us a preview of the significant advancements to come. If life exists elsewhere in the universe, it addresses one of science's most pressing questions. Life might be abundant throughout the cosmos, or we may be entirely alone, isolated on a singular planet in deep space. Either way, profound philosophical and psychological shifts among humanity are likely necessary for its eventual resolution. The search for extraterrestrial life has captivated humanity for centuries, inspiring countless stories and theories. As we advance technologically, our understanding of the universe grows, revealing new possibilities for life beyond Earth. Space telescopes like the JWST enhance not only our ability to detect distant planets but also our capacity to study their atmospheres, helping scientists identify potential biosignatures. Moreover, the exploration of exoplanets fosters collaboration across the global scientific community. International partnerships in space research promote knowledge sharing and resource pooling, increasing the likelihood of significant discoveries. These cooperative efforts also enhance public interest and engagement in space exploration, as findings are often shared widely, sparking curiosity and imagination. Ultimately, the philosophical implications of discovering life elsewhere provoke deep reflections on our existence. The revelation of alien civilizations would transform our understanding of life's purpose. Such questions challenge us to rethink our role in the universe and our relationship with our home planet. As we continue refining our technologies and methods for exploring the stars, each new discovery brings us closer to answering the age-old question: are we alone in the universe? The journey ahead is filled with potential, driving the quest for knowledge and understanding.